Imagine this. We didn't find an asteroid on a collision course. We built a test anyway. A spacecraft, a target, and one clean question. Can we change an asteroid's path on purpose and measure it? DART wasn't about explosions. It was about physics you can't argue with. A hit, a plume, and an orbit that visibly changed. Tonight's case file is the full story, why NASA chose Dimorphos, how the strike actually moved it, and what this proves and what it still doesn't. Part 1 starts with the simplest idea in planetary defense. If you can change an object's velocity by even a tiny amount early enough, you can change where it ends up later by a lot. That's the core of the DART mission. Not drama, not predictions, just a controlled test. And the test needed a target that was safe, measurable, and scientifically clean. So NASA didn't pick a random asteroid. They picked a system with a built-in ruler. A binary asteroid, one larger body and a smaller moon orbiting it. Because if you hit the moon and its orbital period changes, you can measure that change from Earth with incredible confidence. That moon was Dimorphos. The larger asteroid was Didymos. Think of Didymos as the anchor and Dimorphos as the clock hand. Why is a binary system so perfect for this? Because measuring a tiny change in an asteroid's orbit around the Sun is hard. But measuring a change in a small moon's orbit around its partner can be much easier. Here's the trick. As Dimorphos orbits Didymos, the brightness of the system changes in a predictable rhythm. When the moon passes in front, you get a dip. When it passes behind, you get another dip. Those repeating dips let astronomers time the orbit like a stopwatch. So before the impact, astronomers established a baseline. How long does Dimorphos take to go around Didymos? Then DART would strike Dimorphos and the question would be simple. Did that time change? No interpretation wars. No, maybe. Either the period shifts or it doesn't. Now what exactly was DART trying to do physically? A kinetic impact. No explosives, no nuclear device, no sci-fi tricks. Just momentum, mass times velocity. DART was a compact spacecraft moving extremely fast. When it hit Dimorphos, it transferred momentum into the asteroid, giving it a tiny change in velocity. But the real genius is that the impact isn't just a billiard ball collision, because the strike kicks material off the surface, dust, rock, debris. And that ejecta acts like a reaction engine in reverse. Material flies out one way, the asteroid gets pushed the other way. So the total effect can be larger than the spacecraft's momentum alone. That amplification factor is one of the most important lessons in asteroid deflection. But to measure that amplification, you need to control the variables as much as possible. That's why the mission was designed like an experiment. Target selection mattered. Dimorphos had to be small enough to move measurably, but large enough to be a meaningful test. The system had to be observable from Earth during the event. And it had to pose no threat to our planet because this was not a last-minute emergency. It was a rehearsal that would teach us how real asteroids respond when you hit them. Because hit an asteroid sounds simple, until you remember asteroids aren't steel spheres. They can be solid rock, They can be cracked. They can be a rubble pile held together by weak gravity. And your deflection outcome depends on that structure. The same impact can behave very differently on different bodies. So DART was also testing something deeper. Can we predict the result before we do it? Engineers build models, impact physics, ejecta behavior, momentum transfer. But models are only as good as the real-world data you feed them. Before DART, we had impacts in the solar system, but not a controlled deflection experiment with a measurable orbital outcome. This is why planetary defense is partly astronomy and partly engineering. Astronomy finds and tracks objects. Engineering decides what to do about them. DART sat right at that boundary, a mission designed to produce a number. How much did the orbit change? And because it was a binary system, that number wouldn't be subtle. If it worked, the orbital period would shift enough that telescopes on Earth could confirm it. Now let's talk about the approach. A mission like this isn't just aim and hope. By the time DART was close, the target was basically a moving speck, and the spacecraft had to hit the smaller moon, not the larger body. So DART used autonomous navigation in the final phase. In simple terms, it looked at the system, recognized which dot was Dimorphos, and steered itself into a direct impact. That matters because in a real emergency you may not have time for constant manual corrections. Autonomy is part of planetary defense because targets are fast and small, and the final approach is unforgiving. Also, the last minutes produce critical imagery, useful not just for the public, but for science. Surface texture, shape hints, approach geometry. Those details help interpret what happens after the strike. And DART wasn't alone in observation. Earth-based telescopes formed a coordinated campaign, watching the system before, during, and after the impact. This is another reason the mission was so valuable. It tested the global response network. Different telescopes, different wavelengths, different strengths. Some could track brightness changes precisely. Some could image the evolving dust plume. Some could measure spectral hints about the material. If you want to understand the impact, you don't just need the moment of collision. You need the aftermath, how the plume expands, how fast it spreads, how the brightness changes, and how the orbit timing shifts night after night. In a way, DART was an impact plus a full forensic investigation. So what was the success metric? Not did it make a crater, not did it look cool. The metric was orbital period. If Dimorphos slowed down or sped up in its orbit, even slightly, the timing of those light curve dips would change. That change is measurable, repeatable, and independent of anyone's opinion. And importantly, a period change tells you the direction of the effect in a practical sense. DART's impact was designed to alter the Moon's motion around Didymos, shrinking the orbital period. It's like nudging a runner on a circular track so the lap time changes. Now here's the key. Even if you know the spacecraft mass and speed, the ejecta contribution is the wild card. A hard, solid surface might eject less. A loose rubble surface might eject more. So the same hit can produce different levels of orbital change. This is where the words rubble pile matter. Many small asteroids are not monolithic boulders. They're collections of rocks and dust loosely held together by gravity and tiny cohesive forces. If that's your target, an impact can behave like a punch into gravel. You can throw out a large cloud of material, and that cloud carries momentum away. That increases the deflection effect, but it also makes prediction harder. So DART was not only proving we can move something, it was also sampling asteroid geology in the most direct way possible by hitting it and watching how it reacts. That reaction teaches us how future deflection missions should be designed. Do we need heavier spacecraft, multiple impacts, reconnaissance first? Or does ejecta amplification do more work than we expected? Now pause and notice something. This entire experiment is about time. Planetary defense isn't about last-minute heroics. It's about early detection and small changes. If you know years ahead that an object might be a threat, you have options. A tiny velocity change applied early can become a huge miss distance later. That is why surveys, tracking, and orbit refinement matter as much as deflection technology. DART sits on top of that entire pipeline. It's the action tool, but you can't use the tool if you don't have the target. So in a real scenario, the story begins long before impact: discovery, follow-up, orbit refinement, uncertainty shrinking. Part 1 is building that foundation because Part 2 will focus on what happened after impact and why the results surprised people. Before we end Part 1, there's a final piece: why this test matters beyond asteroids. It's a demonstration of controlled intervention in space. Not by pushing with engines, not by grabbing with arms, but by applying a physical impulse to a natural object and measuring the response. That concept scales. Maybe not for every object, maybe not in every scenario, but it's a real tool in the toolbox. And it's measurable in a way the public can understand. You can say, the orbit changed, the period is different, the system behaves differently now. That clarity is rare in space mystery stories. So when people ask, did DART really move an asteroid? The answer is, it was designed so we wouldn't have to guess. We built the ruler into the target itself. So here's the Part 1 summary, clean and simple. Didymos is the primary asteroid. Dimorphos is its small moon. A binary system creates a natural stopwatch through repeating brightness dips. DART was a kinetic impact experiment: transfer momentum and amplify it through ejecta. The goal was not spectacle, it was a measurable change in Dimorphos's orbital period. Autonomous navigation in the final approach proved we can hit a small moving target reliably. A global observing campaign turned the impact into a forensic dataset, not a single moment. That is the setup. Now we're ready for Part 2, the impact itself, the plume, the unexpected scale of the change, and what that tells us about asteroid structure. And one more thought before we transition. A lot of people assume planetary defense means deflecting something at the last second. But real defense is boring. It's early alerts, patient tracking, probability updates, and small controlled interventions. DART was boring in the best possible way, because if you can turn a catastrophic scenario into a routine engineering problem, you've already won. So keep that frame in mind as we go into the impact. We're not chasing a story, we're watching an experiment. Next, the collision. What the cameras saw in the final seconds, what the telescopes saw in the hours after, and the one number that mattered most, how much the orbit period changed. Part 2 begins in the final minutes. This is where the mission stops being a plan and becomes a point of no return. DART is closing on a target that is still, in human terms, almost nothing. 2 dots, one bigger, one smaller. And the spacecraft has to hit the smaller one, Dimorphos, dead on. There's no soft landing option, no braking, no second pass. The entire strategy depends on a clean transfer of momentum, which means one thing: impact. So in these last moments, the navigation system is doing something quietly incredible. It's identifying the correct target, updating its aim, and steering into a collision at extreme speed. And that's the first success of DART that people forget. Before we even talk about the orbit changing, we proved we can hit a small moving body with precision. Now imagine the geometry of the hit. Dimorphos is not a marked bullseye. It's a rough, irregular body with weak gravity. The surface isn't steel, it's likely fractured, dusty, and uneven. So the moment of impact is not like striking a wall. It's more like striking a mountain of loosely packed rock, except the mountain is in microgravity. That matters because microgravity changes everything about debris. On Earth, dust falls back. In space, it can expand into a giant, evolving plume. And the plume is not just a visual, it's part of the physics. Every grain of material thrown outward carries momentum away, and the asteroid system responds with an opposite push. So the impact has 2 components: the spacecraft's momentum and the ejecta momentum. Right after impact, the most important question is not, did it make a crater? The question is, how much momentum actually coupled into the target? Engineers describe this with a simple idea: amplification. If you hit and nothing comes off, the push is basically just the spacecraft. But if the surface blasts material out into space, the target gets an additional shove. You can think of it like recoil. Not because something exploded, but because the physics is the same. Mass leaves in one direction, the remaining body gets momentum the other way. This is why in asteroid deflection, the surface matters as much as the spacecraft. A dense monolith and a loose rubble pile do not react the same way. And DART was designed to reveal that difference in the only language that counts: measurable orbital change. Almost immediately, telescopes saw the system change in brightness. A dust cloud began to expand, and over time, that cloud didn't just fade, it evolved. That evolution tells you about particle sizes, speeds, and how easily material was excavated. Fine dust behaves differently than large chunks. A strong ejecta response suggests the surface was not a single solid slab. It suggests a lot of loose material was available to be launched outward. Now here's what makes this so valuable. You can photograph a dust plume, but you can also measure it in a more disciplined way by tracking the system's brightness and its changes night after night. and while the plume is dramatic, it is still only supporting evidence. The mission's true scoreboard is the orbital period of Dimorphos. So how do we measure that period change in practice? We go back to the built-in stopwatch, the light curve. Before the impact, the binary system had a stable rhythm, dips and rises that repeat as Dimorphos orbits Didymos. After impact, astronomers watch for the same pattern. If the orbit is tighter or faster, the timing shifts. And this is where DART becomes unusually clean as a story, because the outcome is not hidden in a noisy dataset. If the change is large enough, it shows up as a new rhythm. That's exactly what happened. The orbit period changed measurably by a substantial amount on the scale of tens of minutes. Not seconds, not maybe, a real shift. Now, pause and appreciate what that means. We applied a tiny push to a body hundreds of millions of kilograms in mass, and the system's orbital motion changed enough that humans with telescopes on Earth could detect it. That is the proof of concept for kinetic impact. Not that we can destroy an asteroid, not that we can make it disappear, but that we can modify its trajectory in a controlled, measurable way. And that's why the outcome matters for defense. In a real scenario, you don't need a huge change in speed. You need a small change early enough that time does the rest. So DART's result is not a headline trick. It's a demonstration of a real lever. But part 2 is also about the surprise. Many people expected a modest change based mostly on the spacecraft's momentum. Instead, the measured orbital change was larger than that simple collision picture would suggest. And the reason is exactly what we've been building toward: ejecta. The impact produced a strong mass ejection response, and that ejection carried momentum away. In deflection science, there's a practical way to express this. How much bigger was the total push compared to the spacecraft alone? You don't need the exact equation to understand it. If the target throws out a lot of material, the target gets a bigger shove. So DART didn't just hit. It dug in, it excavated, it kicked the surface hard enough that the asteroid system reacted like a springy, granular object, not a rigid rock. This leads to the next crucial question: what does that imply about Dimorphos itself? It implies structure. Not in the sense of a clean building plan, but in the sense of how the body is held together. A rubble pile can absorb an impact differently. It can allow deeper penetration, it can release a larger volume of material, and it can create a plume that persists and spreads in ways a solid surface might not. It also implies that real deflection planning cannot rely on one universal number. You can't assume every asteroid will respond like Dimorphos. Some will be denser, some will be looser, some may have boulders on top of fine regolith. Some may be rotating faster or have different cohesion. So DART's surprise is both good and humbling. Good because it shows the technique can be powerful. Humbling because it shows prediction needs real physical knowledge of the target. Now there's another layer. What exactly changed? We say the orbit changed, but the details matter. The measurable result is the period, the time it takes for Dimorphos to go around Didymos. A shorter period means the orbital configuration changed in a specific direction. That tells us the impact delivered a velocity change component that altered the Moon's orbital energy. But the orbit is not the only thing that can change. A strong impact can also alter rotation state, surface slope stability, and how material migrates afterward. In microgravity, landslides can happen slowly. Dust can loft and resettle. Some of these changes are hard to confirm from Earth alone, which is why follow-up missions matter. Because the orbit is the headline, the geology is the lesson. So what did the images and observations give us besides the period change? They gave us a story of material, what the surface might be made of, how easily it ejects, how the dust behaves. When you see a plume expand and persist, you can infer that a lot of fine material was mobilized. When you track its evolution, you can estimate velocity ranges of the debris. And when different telescopes see different structures in the plume, you can build a model of how the impact excavated and launched material. But here's the key discipline again. We don't turn those visuals into fantasy. We use them to constrain parameters. The plume is not mystery, it's a physical trace, a fingerprint of how the target responded. And the fingerprint strongly suggests the ejecta contribution was significant, helping produce the large period change. Now we have to address the question people always ask. Could this kind of impact accidentally make things worse? The honest answer is, the details depend on the scenario. If you are trying to deflect a real threat, you must ensure you understand the orbit well enough that your intervention moves it away from an impact corridor, not into one. That's why orbit refinement and prediction are not optional. Also, fragmentation risk matters. DART did not aim to shatter the asteroid into many dangerous pieces. It aimed for a momentum change. But a target with unusual structure could respond differently, and you need mission design that accounts for that. So DART proves the basic tool works. It does not prove every asteroid can be deflected the same way with the same risk profile. That's why Part 3 will be about what comes next: reconnaissance, follow-up missions, and building a complete defense workflow. For now, keep Part 2's main takeaway sharp. The impact worked, and it worked strongly because the target gave us ejecta amplification. That means kinetic impact is not just hit it harder, it's hit it correctly and understand what you're hitting. The same spacecraft could produce different results on a different asteroid. So, if you ever hear someone talk about deflection like it's a single trick, that's a warning sign. The trick is a system: detection, tracking, modeling, target characterization, intervention, and verification. DART was the intervention plus verification. And the verification was the cleanest part, a new orbital period measured by many independent observers. That is what makes this case file different from so many space mysteries. Here, the universe answered back with a number. So let's summarize the surprise without hype. We expected momentum transfer. We got momentum transfer plus a strong ejecta response. We expected a measurable change. We got a clearly measurable period shift. We expected a demonstration. We got a dataset, plume evolution, brightness changes, and orbit timing. And the deeper lesson is this. If you want to defend a planet, you need both tools and truth. Tools are spacecraft. Truth is characterization. Because you don't deflect an asteroid in the abstract. You deflect this asteroid with this structure on this orbit at this time. DART moved the conversation from "could we do it" to "how do we scale it responsibly?" And that sets up part 3, what the next missions must measure and what a real response would look like if a threatening object were discovered. Before we transition, one final point: public perception. People saw the impact as a moment. But in planetary defense, the moment is the smallest part. The real work is what comes before, discovery and tracking. And what comes after, verification, modeling, and learning exactly why the response was the way it was. That's why follow-up missions exist. Because seeing a plume from far away is not the same as measuring the crater, the mass distribution, the surface strength, and the internal structure. Without those measurements, you can say it worked, but you can't fully predict the next one. With those measurements, you turn one success into a repeatable capability. And that is exactly the arc of Part 3. From one impact to a long-term defense system. Next, Part 3. What this means for real threats. Why reconnaissance may be the most important missing piece. How you decide when to hit, how many times, and with what confidence. And we'll look at the practical checklist. The minimum data you must have before you intervene, the measurements you must collect afterward, and the mistakes you cannot afford when the target is not a test. Because DART proved the lever exists. Part 3 is where we turn one successful experiment into a real capability. Because DART did something historic. It changed an orbit on purpose. But planetary defense is not one hit. It's a pipeline. A pipeline has stages: discovery, tracking, risk assessment, decision, mission design, intervention, and verification. If any stage is weak, the whole system becomes guesswork. So the question now is not, can we hit an asteroid? We already proved we can. The question is, can we do it with the right target knowledge, at the right time, with the right confidence, under real-world constraints? That is what Part 3 is about. Building the rules around the lever DART just demonstrated. Start with the most important concept in defense: lead time. If you discover a threat early, you don't need a dramatic push. A tiny change in velocity, applied years in advance, becomes a huge miss distance later. But if you discover a threat late, your options shrink fast. You might need multiple impacts, heavier spacecraft, or entirely different strategies. So the hero of planetary defense is often not the deflection mission at all. It's the survey system that finds objects early and the follow-up network that refines their orbits. In other words, DART is the tool. But early discovery is what gives the tool room to work. This is why improving detection and orbit refinement is as critical as building interceptors. Because you can't deflect what you can't predict. Now let's talk about the problem people underestimate: uncertainty. When you first discover an asteroid, its orbit isn't a single line. It's a cloud of possibilities. As you collect more observations, that cloud shrinks. But until it shrinks enough, you may not know whether an object will hit, miss, or pass dangerously close. And here is the critical point. If you intervene while uncertainty is large, you can accidentally move the cloud in a way that complicates prediction. So intervention needs strong tracking and strong modeling. DART avoided this problem by choosing a safe target. But a real defense scenario won't be that clean. You'll be making decisions under uncertainty, public pressure, and strict timing. That's why DART's biggest long-term value is not only the orbit change. It's the data that helps us reduce uncertainty in future deflection predictions. So what data are we missing after DART? We know the orbit changed. We saw the plume. But we don't yet have the full, close-up forensic report on the target. To predict deflection outcomes reliably, we want to know things like the mass of the target, its density distribution, its surface strength, its porosity, and the shape of the crater, because the same measured orbit change could be produced by different combinations of factors. Was the surface extremely loose? Was the crater larger than expected? Did the impact excavate deep material? Did the debris leave at high speed or low speed? These details matter because they control the ejecta momentum contribution, the amplification that made DART so effective. Without close-up measurements, you can celebrate the result, but you can't fully calibrate the models. That's where follow-up missions come in. The next step is not hit again. It's measure what we did. A close-up mission can map the impact site, measure the crater, estimate the mass of Dimorphos, and characterize the surface in detail. It can also measure the binary system's gravity field and refine the orbit in ways ground telescopes cannot. Why does that matter for real defense? Because a real threat asteroid might be discovered with limited time. You may not have the luxury to send a slow reconnaissance mission first. But if you've already built a library of impact response types from previous experiments, your predictions become better. Think of it like medicine. One clinical trial is not enough. You want a body of evidence that tells you how different patients respond. Now let's outline the real-world decision problem. Say an asteroid is discovered and the risk probability is small but non-zero. When do you act? Act too early and you might spend huge resources on a threat that disappears with better data. Act too late and you may lose the lead time that makes small deflections sufficient. So defense planning needs thresholds, probability thresholds, uncertainty thresholds, and time thresholds. DART helps here because it validates that kinetic impact can be part of a standard response. But DART also warns us the effectiveness depends on target properties. So mission design must be adaptable. In some cases, one impact may be enough. In others, you might need multiple impacts in sequence. In others, you might need a different tool entirely. Let's talk about the different tool question carefully. People often jump straight to extremes, like nuclear options. But the practical toolbox is broader. Kinetic impact is attractive because it's simple, testable, and uses existing technology. Other concepts include slow push methods like gravity tractors or surface modification concepts that change how sunlight pressure acts. Some methods require long lead times but offer fine control. The point is, defense is not one trick. It's choosing the right intervention for the object, the orbit, and the available time. DART's role is to make one major option real and measurable. It transforms kinetic impact from a theoretical idea into a demonstrated technique. That matters because in a real scenario, you don't want your first attempt to be on a real threat. Now here's the practical lesson DART taught us about mission design. If ejecta amplification dominates, then the impact angle, the surface type, and the local terrain can change the outcome. A hit into fine regolith could produce a huge plume and a strong shove. A hit into bare rock could produce less ejecta and a weaker shove. A hit near a boulder field could behave differently than a hit into smooth terrain. So to maximize predictability and effectiveness, you may want better target imaging before impact, better shape models, better spin state knowledge, and better surface characterization. This is why reconnaissance matters even when you plan to hit quickly. Even a short flyby companion spacecraft or a small observer CubeSat could dramatically improve your understanding before the strike. In short, DART moved the orbit, but it also exposed what we still need to know to move orbits reliably. So let's build the minimum viable defense checklist. If a real threat appears, what must you know before you intervene? First, the orbit refined. Not just a single path, but a well-constrained uncertainty region. Second, the object size and approximate mass. Because momentum transfer depends on mass, and mass depends on size and density. Third, the rotation state. A fast rotator or tumbling object can change what aiming means. Fourth, basic structure clues, monolith or rubble pile. Even crude estimates help you predict ejecta behavior and coupling efficiency. And fifth, time. How many years, months, or weeks do you have before the risk window? Time determines what missions you can physically launch and execute. Then comes the intervention plan. If you choose kinetic impact, you must define success in numbers. How much delta V do you need? What miss distance do you want? What is your acceptable risk that you underperform or overperform? Because overperform can be a problem too, if it moves the object into a different corridor of close approaches. So you design with margins and verification. This is where DART's binary target design shines as a teaching tool. It shows the value of having a clear verification method. For a single asteroid, verification may require radar observations, long-term tracking, or a dedicated observer spacecraft. You have to plan verification as part of the mission, not as an afterthought. Because if you don't verify, you don't know what you achieved, and you can't plan a second step if you need one. This is also where public communication matters. In a real threat scenario, people will demand certainty. but science deals in probabilities and confidence levels. So, a mature defense system needs clear messaging. What we know, how well we know it, what we did, what we expect, and how we will confirm it. DART is a rare gift because it allows you to demonstrate the concept without the fear. You can educate the public using a safe test. You can show that the method is not magic, it's not luck, it's measurement, and that education matters. Because in a real emergency, trust and understanding will be part of the response infrastructure, just like rockets and telescopes. DART helps build that trust by delivering a simple, undeniable outcome: the period changed. Now we can answer the core question of this case file. What did DART prove? It proved we can navigate to a small asteroid moon and strike it precisely. It proved that a kinetic impact can measurably change an orbit. It proved that ejecta can amplify the effect beyond the spacecraft's momentum alone. And it proved that Earth-based observers can verify a real orbital change through careful timing. But here is what it did not prove. It did not prove that every asteroid will respond the same way. It did not prove that prediction is solved. It did not prove that a single impact is always enough. And it did not replace the need for early detection and reconnaissance. So DART is a milestone, not a finish line. A proof that the lever exists and a reminder that levers still require engineering. So what comes next in practical terms? More tests, better surveys, and better characterization. We need to find more near-Earth objects earlier and track them longer. We need more radar opportunities when objects pass close enough. We need missions that visit asteroids and measure their internal structure, not just their surface. Because planetary defense is a statistics game as much as it is an engineering game. The more you learn about the diversity of asteroid types, the better you can predict the response for the next one. DART gave us one powerful data point. The next goal is to build a dataset large enough that deflection becomes a disciplined field, not a one-off victory. And that is how you go from a single spectacular test to a stable capability. Repeatable methods, verified outcomes, and models that earn trust through evidence. Let's close part 3 with a simple way to remember the lesson. Discovery gives you time. Time gives you options. Options require knowledge. Knowledge reduces uncertainty. Reduced uncertainty allows intervention. Intervention must be verified. And verification feeds back into better models for next time. DART sits inside that loop. It's not the whole loop. But without DART, the loop had a missing link, a demonstrated, measurable deflection step. Now the link exists. The job is to strengthen the rest of the chain. Because the day we discover a real threat, we won't want theory. We'll want procedures. And procedures are built from case files like this: observations, outcomes, and lessons that can be repeated. So that's the case. A spacecraft, a target, a controlled hit, a measurable orbital change. Not a movie scene, an experiment that worked. If you want the one-line conclusion, DART proved we can nudge a celestial body and the universe will answer with a number. The rest is building the system that makes that nudge reliable when it matters. Next time we open a new file, another real mission, another measurable result, and another moment where space stops being a story and becomes evidence.